Thanks very much for the invitation to speak here, and also thanks for the patience as the technical issues around the start of the session got worked out. Thanks everyone for dealing with that also. So I want to talk about an issue that Manish Raghavan, my recently graduated PhD student from Cornell, and I have been working on. Manish is now starting a postdoc at Harvard and then a faculty position at MIT. And one of the things that we've been thinking about over the past several years has been an issue emerging at the intersection of computer science and economics, which is the way in which firms are increasingly turning to algorithms for so-called high-stakes decisions in a number of domains. So there are a lot of cases where a decision that you're trying to make follows the sort of the type of pipeline that's shown here on this slide, in which I have some individual and I have to make a so-called screening decision about them. I may need to make a decision about whether to hire them. If they're an applicant to college, I may need to decide, or to a PhD program, I may need to decide whether to admit them. For a number of decades, the area of credit and lending has evaluated people for a question about successful repayment of a loan using quantitative techniques. Within healthcare, we're increasingly seeing quantitative methods also being used for example, for prioritizing treatment decisions. So all of these are areas where we traditionally may have had a human decision maker evaluating people and then making these kinds of decisions. And increasingly, we're seeing algorithms entering these domains as firms begin procuring algorithms to assist with their hiring decisions, their admission decisions, healthcare prioritization, and other things. Now, what's been interesting here is that the move from human decision making to algorithmic decision making in these kinds of domains is not just a change in scale, efficiency, accuracy, or cost. There are things that actually change qualitatively when we move to algorithms. And I'll mention two of these qualitative changes here. So the first is that the ways in which algorithms make decisions is somehow fundamentally different from the way humans make decisions in these kinds of settings, because the algorithm has somewhere inside it an explicit objective function that it's optimizing, assuming it's built according to any of the standard pipelines for either training machine learning algorithms, building discrete optimization algorithms, or any of the other standard pipelines for building these. Right, it has an explicit set of input variables it's attending to, and an explicit objective function. And if you think about your own experience, for example, I would estimate that most of us on this call have at some point served on a committee where we had to help select people, either applicants to a PhD program, candidates for a job, members of a panel or committee. And if you ask yourself, what was my objective function in doing that, it'd be very hard to write that down with any fidelity. You may have criteria that you agreed on when you and your committee began working on this, but it'd be very hard to say how you actually carried out that objective function with any concreteness. An algorithm, in a sense, almost has no choice but to do that. And that, in a sense, is a qualitative difference, not just a quantitative one. A corollary of this, but important enough that I'll mention as a second point, is that when I create an algorithm using these methodologies, it means I have a classifier whose decisions are perfectly replicable and repeatable, which means if we would like to have multiple parties use the same decision procedure, we can, in a way that's really not possible with humans. Again, I could take a group of humans, I could train them to try to get them to, with some fidelity, follow the same script for making the decisions, but there's no notion that they're actually going to be making the same decisions. There's going to be variation just based on the idiosyncrasies of human decision making. Not so with algorithms, which are actually replicable. So over the past few years, I've been interested in a number of implications of this. One is, which I won't be talking about as much today, is the issue that with the ability to analyze algorithms in this way, this kind of explicitness, there are actually new ways to look for bias and discrimination in these high stakes decisions. The fact that we now have explicit features and explicit objective functions gives us the ability to audit these kinds of decisions for bias in ways that simply aren't possible with human beings. The other point, which Manish and I have begun looking at over the past couple of years is this replicability point, right? This idea that the decision is perfectly replicable across sites. And what that leads to is concerns about so-called monoculture in decision making, right? So this is an issue that we see arising in a number of different areas where algorithms are being employed, where people express the concern that if we truly can have a single algorithm that is making the same decisions for all of us, then, is there going to be a problem that all these decisions somehow become too correlated, right? Have become too similar to each other. What are some of the risks of that? So I want to talk about some of the ways we've tried to build models of this to get at what some of these risks are. Let's start with monoculture. So the term originates in the area of agriculture, where the fear, and this is a fear that's existed for millennia at this point, is that if I plant a single crop species, then that leaves it at risk of eradication by a single pathogen, right? And so if much of my, if much of my business is tied up in the success of this single planting of this crop this season, then it's an enormous risk I'm taking on. Whereas if I plant a heteroculture, right, if I have many species intermingled in what I'm growing, then it's very hard for one pathogen to wipe out more than a fraction of it. So over the past 20 years, people have begun to notice analogies to the way in which this danger of monoculture shows up in computational domains. Probably the most direct analogy is the one that sort of imports the idea of a pathogen directly into the computing setting. So there's within the area of computer security, there's a fear that if we're all running the same operating system on all of our desktops or on all of our devices, all of our phones, then that operating system is susceptible to attack from a single piece of malware that could exploit some security hole, right? Whereas if we're running a diversity of different operating systems, right? If we have competition among multiple vendors of operating systems, then it's harder for a single piece of malware to find a single security hole in all of them. Closer to what I've been discussing so far is the issue of monoculture in prediction methods. And here there's a slightly more indirect concern, but no less severe, which is that if we have a prediction algorithm that's been trained for a certain set of assumptions on a certain set of historical data, and then conditions change dramatically, then potentially the algorithm that we're all using is going to fail, across all of our decisions in some simultaneous way, right? So in particular, this interesting work of Citron and Pascual in 2014, again, made this analogy to agriculture, right? Arguing that like monocultural farming technology in the past, in their case, looking at issues of credit assessment, could somehow fail if there were this sort of single catastrophic change in conditions. And finally, there's another point that comes up, which is that if you're an individual, for example, applying for jobs, and all the employers are using the same algorithm for evaluating hiring, then in some sense you have no recourse, right? If the algorithm doesn't like you, it's not going to like you at all the different places where you apply for jobs. Okay, so this was the picture as Manish and I began looking at it, sort of an emerging narrative of a trade-off between these new algorithms being introduced. They're more accurate than human decision-making. They're more consistent than human decision-making. They avoid potentially many of our errors, even if they still have some errors and biases in them. And so somehow people were imagining this trade-off between this greater level of accuracy on average under normal conditions versus these worse outcomes for specific individuals, and also the susceptibility to catastrophic failure in extreme conditions. And so one thing we were hoping to think about when we looked at algorithms for decision-making, and in particular algorithmic monoculture in decision-making, was to try finding some formalization of this trade-off, that the algorithm is creating better outcomes on average, but it's creating the susceptibility to catastrophic failures and these sort of tail events for individuals as well. But it turns out the picture is more complicated than this. So as we went to construct the simplest model that we could of these kinds of screening decisions, what we actually found was that under really the simplest assumptions that we could create, it's actually possible for monoculture in decision making to lead to worse average outcomes even under normal conditions, right? Even without some kind of catastrophic failure, and even with an algorithm that's individually more accurate, right? So we introduced an algorithm that if you were a single firm, you would certainly want to use it. It's just more accurate in our simple model. But when we have multiple firms and they all use it, then somehow the conditions actually become worse. Okay, and so in a sense, it becomes a kind of brace paradox, right? That improving, right, upgrading the infrastructure is going to make the outcome worse for everyone. So obviously, I need to sort of make precise a number of things here. What are the decisions? What's the average outcome? What are normal conditions, and so forth? And so that's what I wanted to do next, to talk about this model that we created, and then how we arrived at this result. So I want to do this in again, a very stylized model of screening decisions. And so let's pick one of the instantiations of our cases where firms are potentially using algorithms. And let's imagine we're in a kind of hiring scenario. And this is designed, again, in a very abstract way to resemble the ways in which employers are actually beginning to use quantitative tools for hiring and selection. So let's imagine we have two firms trying to hire one candidate each from a common pool of applicants. Each applicant has a true value that's the same for both firms. And the firms have only a noisy estimate of these values. Okay, and from their noisy estimate, they produce a noisy ranking of the applicants, right? So perhaps you could imagine perhaps the sort of true ordering by value is A, B, C, D in alphabetical order. The algorithm is maybe doing slightly better, and it comes up with A, C, B, D. And each of the firms, if they were to work privately without algorithmic assistance, would come up with somewhat noisier rankings. So the firm has a choice, right? So it would like to invest a fixed amount of resources in the selection process, and those resources could either go toward having its own in-house people evaluate applications, like the individual rankings here, the sort of private human rankings, or it could use those same resources to buy the algorithm, and with the algorithm, it would get the algorithmic ranking, right? And so the algorithm ranking would have less noise, but it would be the same ranking for both of them. And the firms will compete by hiring from this set of applicants in a random sequence. And so the firm that's randomly chosen to go first will pick the top of their ranking. And the firm that goes second will look at the top of their ranking. And if that person is available, they'll hire them. And if they're not available, then they will move on to the second choice. Okay, so a couple more things I should make precise here. What do I mean by noisy estimates? What do I mean by noisy ranking? So our results hold in a number of models of noise. I'll, in the talk here, use the following one for concreteness, which is one of the standard models of noisy permutations, namely the Mallows model. And what that assumes is that there's a true ranking, pi star, of the applicants. In my picture, maybe it's 1, 2, 3, 4, 5. There's an underlying transposition distance on pairs of rankings, which says for any other ranking, I look at how many adjacent pairs I would have to swap to convert it from the scrambled ranking into pi star. And the Mallows model simply asserts that there's some parameter phi, so that the probability of any ranking sigma is proportional to phi to the minus transposition distance to pi star. Okay, so the more transpositions you are away, the less likely this ranking is, and it falls off exponentially, right? So it's a model of noise in your ranking. And we can think of phi as an accuracy parameter because, when phi is 1, I get the uniform distribution. And as phi goes to infinity, it becomes a point mass on the true ranking pi star. Right? So the higher the accuracy gets, the higher phi gets, the less noise I have in my ranking. Okay, again, this is the model I'll talk about in the talk here, but we can generalize this result to what we call noisy permutation families, which is essentially any one parameter family of distributions over permutations controlled by some parameter phi. And as such, it also includes certain random utility models in which, for example, the candidates have true base values x1 to xn. I then perturb each xi by adding random noise, and then I sort those perturbed values. And we could also, we're also able to show results for certain categories of those. But for now, let's stick with the Mallows model. Okay, so I've more or less described the setup just to review so this is a game. There are two firms as the players, and their strategies are to either choose the algorithmic ranking or their private human ranking. And again, because they have a fixed supply of resources, we're not really thinking about them having the ability to choose both. That would involve expending twice the resources. So they have to choose one or the other. The algorithmic ranking has an accuracy parameter phi sub a. The private ranking has an accuracy parameter phi sub h. That's less than phi sub a. They then move in a random sequence. The first player hires the top candidate. The second player hires the top candidate on their list if they're available, otherwise the second. And their payoff is just the quality of the candidate they get. And the social welfare is just the sum of those payoffs. And with that, we can now state this result that under, quote, normal conditions, introducing the algorithm can actually make things worse for everybody. That the result we're able to show is that for every private accuracy phi sub h, there exists a higher algorithmic accuracy phi sub a, such that there's a unique dominant strategy equilibrium in this game in which both firms use the algorithm. But social welfare would be higher if both firms use their private rankings. Okay, so the fact that the algorithm is more accurate than the private ranking means that if this were a single player game, right, if you were the only firm in existence and you were faced with a list of candidates, then you should clearly use the algorithmic ranking, right? This would be a straightforward question, which I simply give you two noisy rankings. One has a tighter distribution around the truth. You should pick that one. And yet, when we introduce the algorithm, we have two players. It's still a dominant strategy equilibrium for both players to use the more accurate shared ranking. But social welfare is lower. It would be better if they were to stick to their noisier rankings. Okay. All right, and that's the sense in which adding this stronger option makes things worse, right? So it's not making an assumption that somehow conditions have catastrophically changed. It's not thinking about, the challenge that, a particular applicant like applicant B here has because the ranking for some reason doesn't like them. It's really what's happening in the expected case under this setup. So let me talk a bit about why this is happening, right? So in some sense, this had been the part of the work that Manish and I were hoping to establish some basic monotonicity results so we would move on and do other things. And this was very much not the monotonicity statement that we were expecting. So what's going on here? So to analyze this, it helps to analyze firms moving in a fixed order, right? So the game is to move that the payoffs are determined by moving in a random order. But let's imagine that we said firm one moves first, then firm two. And let's imagine first a world in which the algorithmic ranking and the private ranking have exactly the same accuracy. So if you were a single player, you wouldn't care. And if you were moving first, you actually wouldn't care which one you were using. So suppose firm one moves first, it's indifferent, but let's assume it uses the algorithm. Then what you can show is that actually firm two has a strictly higher expected payoff if it's using its own private ranking, right? This private ranking H for human as a mnemonic for this, okay? And because firm two has a strictly higher expected payoff using its private ranking, that will, by continuity, still hold even if I perturb phi sub h to go slightly up to be slightly more accurate. Okay, so in a sense, this is the non-monotonicity that's going to drive all the other non-monotonicities and what I'm talking about. So let me just give you a brief sketch of why this should be the case. And a sketch of the argument, and it needs a bit of work with the Mallows model to actually prove this, but this is the basic idea. Imagine A1 to AN is the algorithm's ranking, H1 to HN is firm two's private ranking. Now, there are two cases. Either the two rankings agree in their first position, or they don't. Now, if they agree in their first position, then you can show that firm two is actually going to get the same payoff either way, because you basically just take off the first thing. It would have been the same either way, and now firm two is choosing among what's left. But if the rankings disagree in the first position, then effectively, although firm two has to make this choice up front, right? There's some probability that we're in case two, even though it's made this choice up front. And it's now essentially faced with, in one branch, it would have gotten applicant A2, the second one in the algorithmic ranking, and the other gets H1. It's the first one in its ranking. And since phi A equals phi H, and we're drawing from the Mallows model, these rankings have the same distribution. And in the Mallows model, it's better to draw from the first position than the second in this situation. And so in case two, the firm two is going to be doing better if it has its own ranking. So it'll be doing the same in one case, better in the other. Each of those happens with positive probability. And so that's the outcome. Right, so there's sort of a metaphorical story you can tell yourself here, as where instead of two firms, you can imagine, this is a single committee trying to choose two applicants. The committee meets on Monday, and they pick their top choice, and then they discover their top choice isn't available, so they reconvene on Tuesday. and they say, well, let's reevaluate all the candidates, omitting that one. And someone on the committee points out that that's kind of a strange choice because they already had a ranking for Monday. Why not just move on to the second person on their ranking? And so that's the choice they face on Tuesday. Do I just move down the ranking I computed on Monday, or do I recompute my ranking with what's left, introducing fresh noise according to, in our metaphorical story, the Mallows model? And if noise is truly determined by the Mallows model, and if on Tuesday you truly introduce fresh Mallows noise, then in fact, you should actually redecide on Tuesday and you'll actually do better, right? And that's the kind of counterintuitive thing going on here, or at least counterintuitive to us. Okay, that's a fixed order. Now let's talk about two firms moving in a random order, which had been the original setup of the question. So here's the thing that we want to think about. Suppose your competitor, first let's just do a thought experiment. Suppose your competitor is using the algorithmic ranking. Now, when the two accuracies are the same, it's a higher payoff to you to use your private ranking. Why is that? Because either you're moving first and then you're indifferent, or you're moving second, in which case the argument on the previous slide holds. So when they're equal, you have a higher payoff to use your private ranking. Now, if phi sub a, if I keep phi sub h fixed and phi sub a gets larger and larger, to infinity, then eventually gets large enough that I should use the algorithmic ranking, just because the accuracy dominates everything. So that says by continuity, there's some value phi sub a star greater than phi h, where you're indifferent between using the algorithmic ranking and your private ranking. Okay, and so here's the point that I'd like to argue, and I'll show you a sketch of this argument also on the next slide, that at this higher accuracy phi sub a star, right? So we've slid to the right here. At this indifference point, what I'll argue on the next slide is that social welfare is strictly better if both firms use their private rankings instead of both using the algorithmic ranking. Okay, and that's going to use the fixed order argument. I'll sketch that next slide. And again, by continuity, that's going to persist if I increase phi sub a star slightly above phi sub a star, right? So I make the algorithm slightly more accurate still. But now people have a strict preference for the algorithm. And so it becomes a strictly dominant strategy. So the real question is, at this indifference point, phi sub a star is bigger than the private ranking. Why is social welfare better if both firms use their private rankings? So here's the rough argument for this. So let's picture firm one's decision, and suppose firm two is using the algorithm at this indifference point, phi sub a star and phi sub h. So firm one is choosing between a and h. Now, if firm one uses a, let's just declare the payoff to be x. We're just going to name it some variable x. So by symmetry, the social welfare is 2x because both firms are using the algorithm. Now, this is the point at which firm one is indifferent between using its private ranking or the algorithmic ranking. So if it switches to its private ranking, its payoff is still x. That's just by indifference. Okay. Now, suppose firm two were to now switch to using the human ranking. And firm one is using the algorithmic ranking, is now using its human ranking. If firm two switches to its human ranking, well, then firm one is faced with weaker competition, because firm two, if firm one moves first, it's indifferent. And if firm two moves, if firm one moves second, firm two moves first, then firm two is using a noisier ranking. And so it's depleting the pool slightly less because it's more likely to pick someone worse when it draws its candidate. And therefore you have a slightly better pool of options when you go next. This part takes, again, some analysis of the Mallows model, but this in fact is true. So firm one's payoff now goes up to y. So now we have a situation where both firms are using h. We decide firm one's payoff is y, and firm two's payoff is also y by symmetry. So social welfare is now 2y instead of 2x. And so it's greater when they use h rather than a. Okay. And that's, again, with some amount of analysis of these noisy permutations to be filled in, is how we get from the fixed order argument up to this argument that there's a value for phi sub a where the unique dominant strategy equilibrium is going to be worse for social welfare, right? And so fundamentally the non-monotonicity it's coming from is that when you're moving second, even with equal accuracies, you actually do better to re-randomize, redraw from the distribution than to just continue following the same ranking. So I want to mention a couple of extra extensions, and then I'm happy to take questions. So one is the question of multiple firms, right? So we've talked about two firms, and a natural question is, what if more than two firms are engaged in all of this? And things actually get fairly complicated here. Um, so we don't have actually. So beyond two firms, it's an open question to actually uh, prove that the brace paradox happens for all numbers of firms and all values of the private accuracy phi sub h. We can show this computationally in the sense that you can set up the game and you can compute the equilibrium. You can find there is now a dominant strategy equilibrium where firms choose the algorithm, and yet social welfare is worse. But it's an open question to actually prove that for arbitrary numbers of firms. Just to show some of the difficulty in doing this analytically, let's again go back to the basic step, firms moving in a fixed order. Okay, so K firms moving in the order 1, 2, 3 up to K. And so the strategies of these K firms moving in order, right? They're now just choosing sequentially. So there's some, fixed optimal choice that each one makes by induction. And I can write their optimal sequence as a sequence of K symbols, each of which is either A or H, right? Algorithm or private human ranking. That says that I can take the phi H, phi A plane, right? The two parameters that define this problem for a fixed number of firms K. And I can actually label it with the sequence of optimal strategies that they're going to go through as they choose in order. Right? So imagine the plane, and it's sort of colored with these bit strings of phi sub H and of H's and A's for the order in which they're going to do it. Right? In the two-player case, that just means, AA, AH, HA, and so forth. But with higher numbers of firms, it could be something else. Now, one thing we can prove with arbitrary numbers of firms is that when the private accuracy is higher than the algorithmic accuracy, it is uniquely optimal for all firms to choose H, because they get the benefits of re-randomizing and the higher accuracy. That takes a proof, but that indeed holds. But what about the hard case, right? The sort of paradoxical case for us, when the algorithmic accuracy is higher than the human accuracy. What happens then? So let me show you the answer for 5 firms on the next slide. Okay, so this is 5 firms, 6 candidates, and this is a coloring of the plane by what string of A's and H's holds for every value of these parameters. Okay, and this is what we get. And it was, to say the least, a bit more complicated than we were expecting. So this is the region where phi H, this light blue thing down here in the lower right, the region where phi sub H is higher than phi sub A, and you just want to, everybody uses the all H choice. When phi sub A gets high enough up here, then indeed everybody wants to use all A, because the accuracy dominates. It's this region here where we get these non-monotonic effects. And so if you pick some value of phi sub H and you just start walking upward, you encounter a whole set of other bit strings, right? Strings of A and H alternations that the firms are using. And you could ask yourself, can I detect any pattern in what these are so that I could at least make a conjecture about what I'm supposed to be proving in the case of these higher numbers of firms? So, we could try this out. So the instant we cross over this line, the first person uses A, because the first player doesn't see its competition. They just want the most accurate thing. So we know we're switching over to A for the first player. Beyond that, we start with all H's. And then as we move upward, these are labeled in the order of moving upward. We next flip this to an A, then that flips to an H, this goes to an A, that goes to an A, they all flip, and this becomes an A. It actually turns out when you do this, and this is computational results, right? So these are what we see when we actually compute this out. What it's doing is it's actually counting in binary, right? So if I treat A as 0, H is 0 and A is 1, it's counting 0, 1, 2, 3, 4, 5, 6, and so forth. It's actually implementing a binary odometer as it goes up, eventually rolling all the way over to the all ones, which is everybody using the algorithm, right? And so all 2 to the k minus 1 values are showing up with A in the first position, and everything else implementing this binary counter, right? And this is naturally was not what we guessed when we first created this plot. And it's sort of interesting to think about what's going on here, right? And some partial analysis here suggests that what's happening is that the re-randomization is being traded off against the loss in accuracy, and obviously, sort of as people ahead of you deplete the pool, with greater fidelity using the algorithm, you need more re-randomization. As people use more re-randomization, you have the ability to go back to the algorithm. why this is implementing a binary counter is something we don't really even have sort of a good heuristic sense for. Okay, and so with that, I'm basically at time, so I want to wrap up. This notion of algorithmic monoculture is something which has been an idea that's been around for quite a while in the computer security literature, where the idea really was these sort of catastrophic threats that were sort of outside your working assumptions. What's happening here, though, is something kind of more surprising, more subtle, and maybe more pernicious, that the introduction of more accurate decision making is causing people to converge on shared decisions that are actually worse on average for everybody. And so I think, it's interesting to sort of ask, we can sort of identify the underlying probabilistic reason why this is happening, the lack of re-randomization, but it still somehow seems subtle, fundamentally, what's going on here. And we've chosen a very, very simple case of selection by firms from an applicant pool. But there's an interesting question about correlated optimization, for example. In any case where many firms are optimizing, producing some kind of shared infrastructure for society, in this case, the selection for the job market, and to ask when the correlation of more accurate algorithms is going to create worse shared infrastructure. There are a number of further directions that we could think about. I've shown you some of the open questions related to multiple competing agents, which seem to get quite complicated within our model. There are cases in which agents might actually choose how to partition it into groups and only share models within their own group. So I have neither complete independence nor complete convergence, but some kind of groups. And then I have an interesting coalitional game structure that my student Kate Donahue and I have been looking at. And again, this issue of, in general, the ecosystem of decision-making and optimization, what effect monoculture has, I think, is clearly an interesting and surprisingly subtle issue that I think will be very interesting to look at this boundary of computing and economics going forward. Thanks very much.
Thank you, John. And I have a question from Peter Crampton, who, by the way, you got some bonus few minutes just because we want to round and to start the next one at 11 o'clock sharp.
Okay.
So the question of Peter is, if there are many firms, monoculture is limited by competition. Think Michael Lewis, Moneyball, baseball teams were all using the same algorithm, human scouts. The Oakland has decided to think differently and use an algorithm. They did much better because they were able to pick the players who were undervalued by the human scouts. Notice the success comes from from the price impact of the others using the same approach. Any thoughts?
Yeah, that's a great question. And the Moneyball analogy is a very interesting one. So let me say sort of how I think there's similarity to what we're talking about here, and then also some interesting differences, which I think would be, which I think your question really raises in a fascinating way. So the similarities, I do feel like a first pass at this is baseball teams were sort of all using the same algorithm, namely human scouts. But on the other hand, given the idiosyncrasy of human decision making, humans were also judging in some sense subjectively. And so two human scouts are going to watch somebody on the field in the minor leagues, and they're going to, or in the farm leagues, and are going to somehow think differently about that same thing that they're seeing. And that introduces the kind of independent idiosyncrasy. Then you can imagine that's the all H situation. One firm now introduces A, which is more accurate. And so it's in this sort of, it's almost in the kind of like the sort of, the world of antibiotics before antibiotic resistant strains emerge, where they have more accuracy and they're basically working independently of everybody else. And so that's clearly a big win. I think we're sort of thinking about the case of the sort of late era Moneyball, where now everybody is using, and suppose everyone now uses the same algorithm. So they all use the same, sort of expected runs earned, sort of all of the kind of Bill James type measures. And if we all sort of naively just use the same formulas, we're going to be in this world of monoculture. And the argument here is that actually may end up producing, obviously we'd have to evaluate it for the case of baseball in particular, which is not exactly the Mallows model and all of the, all the caveats, but it'd be an interesting question, would convergence on the same, Bill James style formulas for baseball result in actually worse average outcomes if we got all the way to everyone using them? Now, there are several things that make this different from the situation we have here. One, not everyone will use the same formula, so even the algorithms will be a little different. And secondly, there's an interesting thing here that doesn't seem, it isn't captured by our model, which is that it's quite possible that the sort of human ranking that they were all noisy offsets from is not the same as the algorithmic ranking that they were all noisy offsets from. And so the move to the algorithm was not just a move toward greater accuracy, but potentially actually a shift from what the base pi star was. And that's of course an interesting thing to think about also. So yeah, I think it's a great domain to think about.
John, thank you so much.